So today I hear, who's taking the big physics test? Okay, half the class. Good. We will make sure not to say anything too critical in the last 5 minutes of class to give those people a head start, and I'll say when everyone can get a head start, so we only interrupt everyone else once. But after that, I'll just do a dance for 5 minutes. How about that? We'll cut the video off then too, so it won't be on YouTube. Okay, so last time in class we talked about, last time in class we talked about the effect of size confinement on wave functions and how organic dyes derive their visible and their electronic absorption from these transitions between wave functions in the occupied, what are called molecular orbitals. So the wave functions are the molecular orbitals to some higher unoccupied orbital, and the energy of absorption is quantized by the particle in a box model to the distance between those energies. And what we're going to find is that the effect of size confinement is consistent across a range of different materials. And today we're going to talk about a particularly interesting type of nanostructure called a quantum dot, which is just a semiconductor nanocrystal. I say just, not just. It's a quantum dot. So you take a semiconductor and you shrink it down. You shrink down the size to 10 nanometers, 7 nanometers, 5 nanometers. Sizes below 10 nanometers, the band gap begins to change appreciably, where the band gap gets larger the smaller the dot becomes. And therefore, the more energy it takes from a photon to excite an electron to a higher energy level from the valence band to the conduction band. And then, as usual, we have process thermalization down to the band edge, and then relaxation of the de-excitation, which corresponds to emission of a photoluminescent photon or a fluorescent photon. So what this is the basis of is quantum dot-based solar cells. So this is an area of research. It was a bit more active in the mid-2000s, but there's still some important research being done on it now. And also quantum dots are useful in bioimaging and display technologies. So what is useful, if we have a quantum dot or a film of quantum dots that can be sprayed like paint on a glass sheet, is that if we have light that's too bright for our eyes to look good in a display, for example, then those quantum dots will absorb the high energy light and re-emit it at a longer wavelength, so a lower energy, larger wavelength, and it's more it produces a more vibrant type of display. So this is actually a question on week 2's homework, which will be posted tonight. And but I'll basically give you all the answers today. So how does size confinement work in 3 dimensions? And the absorption of a quantum dot is a bit like picturing a particle in a 3-dimensional box combined with some complications arising from the fact that we have a positively charged hole left over in the valence band as a result of kicking that electron up to the conduction band, and also that we're in a medium. So we're in a semiconductor medium that has a dielectric constant because it's made of atoms that have charges that can be polarized and can screen electric fields. So we need to take into account all of all 2 of those complications. But first, let's look at what does a one-dimensional particle in a box look like if it's just extended to 3 dimensions. And we'll use Cartesian coordinates, forget spherical symmetry for now. So what is a 3D particle in a box? Look like? So the total energy in 3D is just going to be a sum along the energy in the along the x-axis, the y-axis, and the z-axis. And let's draw our box here. I always get into trouble when I'm drawing in 3 dimensions. So the coordinate system that we'll use here is z going up, y coming out of the board, and x horizontal. And we'll call the lengths of this particular box A, B, and C thusly, where A corresponds to X, B corresponds to Y, and C corresponds to Z. So in order to find the energies, we just add up all of the energies along each axis. So the energy, last time we had n squared h squared over 8ml squared. But if you factor out the h squared and the 8m, and you have nx squared over a squared and y squared over b squared and then z squared over c squared, that gives you the total energy along each axis. So we have h squared, which is Planck's constant, 6.626 times 10 to the minus 34 joule second, over 8 times the mass of the particle, times the quantity nx squared over a squared plus ny squared over b squared and n z squared over c squared. Now, what do the wave functions look like? Well, they look like a 3-dimensional version of the one-dimensional particle in a box wave functions, but in one dimension we can draw these oscillatory sine wave looking wave functions, but in 3 dimensions we don't have a 4th dimension to show gradation, so we have to pick some kind of threshold in order to show where the density of the wave function is going to be the highest. So the ground state, let's draw 3. This is my favorite optical illusion called a Necker cube, where you can't tell if it's facing into the board or out of the board. We'll just stare at it for like 2 minutes and see if you can get the box to interconvert. There it is, okay. Okay, let's draw the ground state. Psi 111 is a spherical blob in the middle. Now really, if I could draw in 4 dimensions, someday I'll be able to draw in 4 dimensions. If I could draw in 4 dimensions, I would show that this is kind of slowly tailing off somehow. But since I can't draw in 4 dimensions, you just have to picture it as a lobe. It's just this lobe where the boundary is not actually a strict boundary of the wave function, but just some threshold. let's look at psi 2, 1, 1, where we have n equals 2 along the x direction. So we have 2 lobes along the x direction. How about psi 2, 2, 2, where we are, where the wave function, or in the excited state along each axis. And what we have here are these lobes, which are toward the corners of the three-dimensional box. Okay, let's talk about quantum dots. So quantum dots, this is even our beta carotene example was not a real one-dimensional particle in a box. It had lots of atoms. We said that this alternating arrangement of single and double bonds gave a completely delocalized wave function. The fact is it doesn't. The electron density is actually somewhat more localized where the bonds are actually drawn than between them, but we said, nah, forget all that. It's completely delocalized. It's not actually. So there was the fudge factor. We said that it was 18.5 angstroms, 1.85 nanometers across, which is a little bit too small than for what a little bit smaller than beta carotene actually is. Just like this three-dimensional particle in a box, we can't map this directly to a system that's actually made of atoms and molecules because we have no dielectric constant here. We have no sea of electrons from which you're promoting one electron in the valence band to the conduction band. So we need a couple of fudge factors in order to get this to apply to an actual semiconductor nanocrystal. Has anybody ever seen, anyone ever Google image searched quantum dots? So if you do, any lab or research organization that works with quantum dots has their own great picture of like 8 vials all lined up next to each other that give you all the colors of the rainbow. I highly recommend that if you haven't seen this, that you do a Google image search for it, and you'll get roughly 900 million different photos of different quantum dot rainbows, basically. Okay, semiconductor nanocrystals. AKA quantum dots. The key is that we are going to account for the fact that there's a hole left behind in the valence band. The material itself that is the dielectric constant course, the effect of size confinement. So why does it matter that we account for the hole left behind in the valence band? Well, the hole left behind in the valence band has a positive charge associated with it. So when you promote an electron from the valence band to the conduction band, there's actually a Coulombic attraction between the electron and the hole that was left behind. And that actually serves to lower the energy and decrease the band gap slightly. That's the Coulombic binding energy. Yeah.
The waveforms we're using here correspond to or various.
They are all they're all wave functions. So any possible wave function will have this form. That could be a wave function of even an unoccupied. So you could have a wave function for two electrons. If one spin up and one spin down, you could have a wave function for an unoccupied molecular orbital. They're just the allowed states in which a confined particle is allowed to have. And in fact, since a quantum dot has spherical symmetry, these won't actually apply. So in my discussion here, I'll just erase these. But this was the extension to 3 Cartesian coordinates. The quantum dot doesn't always have spherical symmetry. In fact, in an example that I'll show on nanocrystal solar cells, they have rod-like or rice-like shapes. And then they don't really call them quantum dots, they just call them semiconductor nanocrystals. Okay, so what we end up having is that the energy of the quantum dot band gap equals the energy of the bulk band gap. This is the energy of a semiconductor of infinite extent. But for our cases, infinite extent is a couple tens of nanometers, while the effects of size confinement on the electronic structure are no longer present. So often we're talking about, this is a very theoretical discussion, but what kind of semiconductor are we talking about? Well, metal chalcogenides, lead sulfide, cadmium telluride are usually the favored materials to be used for semiconductor quantum dots. And let's just say, for example, the band gap of cadmium selenide, and this is sort of the prototypical example, so we'll continue to refer to these numbers later on. The bulk band gap is 1.74 electron volts. So that corresponds to a photon with wavelength 1240 eV nanometers divided by 1.74. And I don't do arithmetic that well in my head, so you can see what we can calculate what that is. Okay. So we have the energy of the bulk band gap. The band gap increases by an amount that is dictated by the particle in a box. And I'm not going to derive this. I'll just show it to you and sort of show you where it comes from. But you will almost certainly derive it in 204, or 104. So you have h bar squared pi squared over 2a squared, where a is the radius of the quantum dot. Times the reduced mass of the mass of the electron plus 1 over the mass of the hole. Wait a minute. What's the mass of a hole? How can the absence of something have a mass? A hole has a special place in semiconductor science because it's a real thing, but it's the absence of something. But you also need electrons to backfill the space where the hole was. So the mass of a hole in a semiconductor valence band is actually the mass of the electron that's filling its place. So as the hole moves, the electrons have to fill in the old spot. Is that okay? Okay, so this is the part of the equation that deals with due to size confinement in a spherical box. How can you have a spherical box? It's a spherical box. Trust me. Okay, then we have minus the energy. So the band gap is lowered by this effect of Coulombic attraction. So what we're going to write here is the Coulomb energy times some fudge factor. Which is 1.8 squared over 4 pi epsilon times epsilon naught times A. Now what are all these terms? 1.8 is the fudge factor, and the rest of this is just Coulomb's law between two free charges. E in this case is the fundamental charge. That is the charge of an electron. Or a hole. Epsilon is the relative permittivity of the medium. Otherwise known as dielectric constant. Can everybody see it if I write down here? So AKA dielectric constant. What are the possible values of dielectric constant? Anybody know? It's dielectric constant of air. 1. So this has to be, or vacuum 1. Air is like 1.000 something. Dielectric constant has to be greater than or equal to 1. In this particular case, the dielectric constant is also dependent on size, but we're not going to worry about it right now, or ever, until the next professor tells you have to worry about it. The dielectric constant is what? The dielectric constant is the ability of a medium to screen charges. So if you have a charge and you're in a very polarizable medium, so dipoles and electron clouds can arrange themselves in such a way to lower the electrostatic energy of a charge, then that charge will have less electrostatic potential energy to interact with other charges. Electrostatic potential energy is something that can be used up in interactions. It's a little bit like your personal bandwidth. If there are a lot of people around you that say want to get your attention, want your autograph, they know I only have so much attention. I only have so much attention. I can only interact with so many people. Just like that, charges and molecules and dipoles have some amount of electrostatic potential energy that they can only use up by interacting with other charges and dipoles. Now, if you're in a high dielectric constant environment, there are a lot of electron clouds and dipoles that interact with this charge that serve to lower its ability to interact with other charges. Yep.
So is that kind of related to the idea that when it's humid out, they're less likely to get static charge and shock someone with, or if it's really dry out?
That's a really good question. The question is, when it's humid out, you're less likely to build up a static charge. You certainly can satisfy charges by having water molecules associate with them. There is probably more to it than that, but I'd need to look it up. Okay, so what's this? This is the permittivity of free space. That's epsilon naught. Also, one pro tip, when watching these videos on YouTube or when listening to the podcast and going along with your notes or my notes, it's very helpful to speed me up because I sometimes talk slow and you've already seen the lecture. So speed it up to like factor of 2, and then when I'm writing long words like permittivity, you don't have to wait there for the next thing. Just, all right, permittivity. Okay, this last term, what is this last term? Last term is due to Coulombic attraction. Due to Coulombic attraction between the electron and the hole it leaves behind. What is the consequence? The consequence is that as the size decreases, the band gap increases. And you can see that by the inverse 1/a squared dependence on the term that increases the band gap, and the 1/a without the square on the term that decreases the band gap. So as the size gets really, really, really small, the band gap goes up and up and up. And what do we expect from the fluorescent photons that a small quantum dot would emit? They would be higher in energy or lower in energy than the big quantum dots? Higher in energy. So consequence, as the radius decreases, the band gap increases. Higher energy of photons. here are 5 quantum dots that have sizes 2 nanometers, 2.5 nanometers, 3 nanometers, 5 nanometers, and 6 nanometers. Not drawn to scale, obviously. Let's imagine that we are irradiating these quantum dots with violet light. And we'll use the Blu-ray wavelength, Blu-ray disc, which is actually violet ray. 405 nanometers. So I got a question in office hours. Why are we talking about wavelengths that are over 100 nanometers? How is that nanoengineering? Well, large particle, and I get it. This is too big. But large wavelengths interact with small bits of matter. And you'll see that now. This 2 nanometer quantum dot will absorb this 405 nanometer photon. Now this 405 nanometer photon happens to be a bit bigger than the band gap, but that's fine because there's a density of states between the band edges. So it will absorb somewhere up here, then it will thermalize back down here, then the electron will go back to the valence band and emit a fluorescent photon. That fluorescent photon is going to have a larger wavelength and smaller energy than the incident photon. So what this does is it emits a photon with a wavelength of 490 nanometers. And this is the lambda max of emission. So this is, if you have a plot of absorption versus wavelength, it's not going to be a straight line because you have a density of states on either side of the band edge. It's going to be a lazy signal. It's going to be a lazy peak, but the peak will be about 490 nanometers. And this is for cadmium selenide quantum dots. Similarly, the 2.5 nanometer photon, oh, by the way, 490 nanometers is something like blue-green. 2.5 nanometer photon, the band gap gets smaller. 530 nanometers, which is solidly green. Three nanometer, you get a 570 nanometer photon, which is somewhere in the green, yellow regime. The 5 nanometer quantum dot, you get a 610 nanometer photon, which is orange. And the 6 nanometer quantum dot, you get a 640 nanometer photon, which is red. Visible range, again, is about 400 to 700 nanometers. And these are the fluorescent the fluorescent wavelengths. So they will all absorb higher energy light, lower wavelength light, but they will emit fluorescent photons of decreasing energy with increasing size. Yep.
If you have quantum dots that are bigger or smaller, you get outside of the visible spectrum.
Yes, the question is, if you have quantum dots that are bigger or smaller, can you get outside of the visible spectrum? You absolutely can. So you can have UV emitting quantum dots, but you have to irradiate them with an even higher energy UV photon. If you have large quantum dots, you can have IR fluorescence. So it's possible to have, we don't usually think of fluorescence as being anything other than visible light, but you can indeed have it. You need a lower band gap bulk semiconductor to start with, because the smallest this band gap will ever be is the energy of the bulk. So you need to, I can't name offhand which semiconductor it would be, but they do exist. Yeah.
So we always need a shorter wavelength, higher energy light we want.
Exactly. We always need a shorter wavelength incident light than the wavelength we want emitted. So how is this useful? Well, quantum dots can be thought of as inorganic dye molecules, but they have the advantage that they are more stable to air. So if you have some beta carotene smeared on a surface, after a while it's going to photo bleach and it won't be orange anymore. It'll be degraded by light and oxygen. Quantum dots are more resistant to oxidation. Usually what happens when you prepare these, because quantum dots themselves are insoluble in solvents, so that makes them not that useful from a manufacturing standpoint. So what you end up doing is you put an organic ligand on them, which could be a phosphine or something. This could be a phosphorus atom that has, say, some hydrocarbon chains coming out of it. And this motif of chemical functionalization allows you to dissolve the quantum dots in an organic solvent. So you can spread them on surfaces like paint and use them in things like display technologies. Okay, I want to give you a couple of technological examples of how these materials are used. And the first one is in an all quantum dot solar cell. And in your homework, I'm going to ask you to look up this paper and just so you have an idea of just how this research is done. You can read the paper or not, or you can just kind of skim and find where the information is. Quantum dot solar cells, which was published first by Gurr et al. This was published by Oliver Sados's group at Berkeley in the journal Science, 2005, volume 310, page 462. And what they did was they built a solar cell on glass. And in the solar cell literature, the light always comes from the bottom. So the sunlight comes from the bottom. On the glass, you have a layer of ITO, which is indium tin oxide, 74% indium, 18% oxygen, 8% tin. All of you have lots of ITO in your smartphones. They're on each side of the transparent display panel. This is used ubiquitously in optoelectronic devices. Then you have a really thin layer of Al2O3. Then you have your quantum dots, and your semiconductor nanocrystals. You have cadmium telluride nanocrystals, 100 nanometers thick layer. And this is that means in 5 minutes the people with the physics exam can leave. Okay, so you have 100 nanometers of the cadmium telluride. This is the P-type material. Don't worry quite about what that is, just it means it transports the positive charges. Cadmium selenide, also 100 nanometers. And in this, and the top, we have just a thin film of aluminum to collect the electrons. So this is N-type. So the electrons go up in this diagram and the holes go down. And when you connect these devices to a load, it can power the load. In this case, the P-type nanocrystals are these rod-like structure, like nanocrystals. They are 100 nanometers approximately in diameter and 1 micron long. And then in this case, for the cadmium selenide, you had these 500 nanometer rice or football-shaped particles that were also about 100 nanometers along the short axis. Now, if you look at the energies in electron volts, what we have is the work function of the ITO. Then we draw the band edges of the N and P type materials. So this is the cadmium telluride nanoparticles here, and then somewhere around here we have the cadmium selenide. And then we have the work function of the aluminum, which is somewhere around here. And so what happens is when a photon comes in, this is sunlight, then one of these electrons in the valence band is promoted after the thermalization process to the conduction, somewhere in the conduction band. And then what happens is that this electron undergoes a photoinduced electron transfer reaction to the conduction band of the N-type material, and then it's picked up by the aluminum. So the electron ends up going this way, and the hole, meanwhile, is conducted out the other way. So the holes go this way. This isn't exactly how solar cells work when they're made of bulk semiconductors. This is sort of a special case. In the case of organic solar cells and semiconductor nanocrystal solar cells, you actually need these two types of materials with these offset band edges in order to allow this photoinduced electron transfer to happen. And I see that people are getting a little antsy, so I'm going to give another example in display technologies, but for the next 30 seconds, I'm going to let the people that need to run across campus to do that now. Okay, how about quantum dot diffuser panels? In LCD displays. How does an LCD display work?
I was going to ask if that electron would have to go up in energy in order to leave the system.
There's actually, this is the top of the work function. It's actually, it's not impossible for electrons to shift in energy a little bit. It's unfavorable, but it happens. So how does an LCD display work? Basically, you have a white light that comes in. You have a rear polarizer. You have a liquid crystal layer that is controlled by a thin film transistor array. Then you have a color filter, which are the RGB pixels. If you take a display panel and you look at it under a microscope, you have little red, green, and blue color filters. Then you have a front polarizer. So in the off state, what happens is that there's no electrical bias on the liquid crystals, but what you have is a textured surface that allows the liquid crystal molecules to align in this direction in the back, and then in this direction in the front. So you have two perpendicular panels that align the liquid crystals. And what are the liquid crystals but an organic molecule this is called 5CB. The 5 means there are 5 carbon atoms out here. The CB, don't worry about it. 8CB would have a couple more carbon atoms. Hint for the homework. So this molecule has a rigid molecular structure, and they align when you have a textured surface on this side and a textured surface on the other side in the opposite direction. It aligns in this quarter helix. Now what happens is that the white light comes in. It's polarized. The white light comes in in all polarizations. It goes through the polarizer, and then it's polarized along this axis, and then it slowly becomes polarized along this axis, goes through the color filter, and then it comes out the polarizer unchanged because it's already polarized by the liquid crystals when it comes out through this axis. When you apply a voltage using the thin film transistor array, you untwist the liquid crystal molecules to some degree, and that degree depends on how many bits your display is. If you have 1 byte, then you have some number fewer than if you have 2 bytes of information per pixel. So as you increase the voltage, you can align you can untwist the helix such that the molecules are all pointed this way. There's no polarization of the light by the liquid crystal layer. And then when it comes through to hit this polarizer in this orientation, in this polarization, then no light comes through because all of it is polarized like this, and it's all blocked. So a liquid crystal pixel that has no voltage applied appears its brightest possible color, and with the strongest voltage possible applied, it's its darkest possible color. Because there's some leakage here, you can never turn an LCD display completely off. That's why new technologies like OLED displays have that's organic light emitting diodes, where each pixel is lit individually. That's why that technology allows you some more contrast ratio, because it's possible to extinguish a pixel entirely. Okay, this part I didn't tell you about. This is the diffuser panel. And in the case of quantum dot LCD displays, you put the white light coming in is of poor quality. It's too high in energy. It doesn't look good to our eyes at the end. If you put the diffuser in, what happens is that high energy light comes in, and those high energy photons, which are undesirable, are absorbed and re-emitted fluorescently by the quantum dots of which this panel, which this panel is coated. They're re-emitted at lower wavelengths, so that when it comes out, the colors align more naturally with the way that our eyes are engineered to perceive color, and that's why it looks better. Thanks very much for your attention. I'll see you on Friday.